All right, so day 1B, so the applications of the parabola. So you've done some practice with parabolas. Hopefully you're an expert on those equations now and the forms and how to find P and the focus and the directrix. Now we want to talk about why do we even care about those, and this is huge. If you didn't already know this, we use parabolas in so many things, especially a lot of stuff in space, directing communications. We use lights, we do this. You know, the headlights in your car kind of use a parabola. Or a parabolic shape. So the main application of parabolas involves their use as reflectors of sound, light, radio waves, and other electromagnetic waves. If you rotate that, so you take that parabola and you rotate it in a 3D shape, it makes like these kind of, I won't say cone, they're not really cone-like because they're curved, but they make paraboloids of revolution. Let me put a parenthesis there. And then if you put a light source back here, so you turn a light on, all the light's going to bounce off those and go out, and actually the light comes out in all these parallel lines. Okay, so you can direct the light and focus it on one area. So think about a spotlight. And it also works in the opposite direction. You know, if radio signals were coming in, this is why satellites are shaped like this. You think satellite dishes are shaped like this. If the signal hits here, it's going to bounce, go right to that point, the focus. If it comes in really close to it, it's going to bounce and come back to it. So basically you get this, all of these radio signals bounce and come back to the same point, and they're extremely intense, and it intensifies and makes the signal stronger, and then the receiver has an easier job of interpreting those waves into TV, radio, sound, whatever it is you're trying to do. So keeping that in mind, think about exactly what we did yesterday. Okay, so on the sidelines of televised football games, the FBTV network probably will exist someday. Everything has its own station now to make money. Uses a parabolic reflector with a microphone at the reflector's focus to capture the conversation. So you can hear from a lot further away if you have one of these handheld microphones. If the parabolic reflector is 3 feet across and 1 foot deep, where should we put the microphone? So how far away from the curved part of this device should we put the microphone? So the way I did it, and you could do it just about any way, but I just thought of this as, here's the top of the device. There's a handle coming down so the person can hold it. And so here would be the vertex of the thing. Somewhere out here is the focus. I don't know where we're going to put it. We're going to try to figure out how far away to put it. I do know that this right here is 3 feet. That's 3 feet wide. So think, that's kind of these points have to be on the parabola. I guess is what it is. We're trying to figure out what kind of a parabola do I need to draw? Well, if the easiest kind of parabola is when the vertex is at the origin, so let's just do this and let's slap down a Cartesian plane and say that's the origin also. Okay. It says that this is 1 foot away. So this is 1 feet deep, 3 feet wide, and we're trying to find the focus. So if the vertex is at 0, 0, then my equation, and since I chose to aim it to the right, it would be y squared. Now if you oriented this going up instead, and said, right here's the origin, the vertex, you could do x squared, and you'll get something very similar. Well, you get the same answer in the end, because the answer is how far away to put it. And this equals 4p times x, because I wanted mine to the right. So a coordinate I know, what would these coordinates be right here? This would be 1 to the right, so that'd be 1, this point right here, comma, and then since this is 3 feet, it'd be up 1.5. So I can use that coordinate right there. When I plug in 1 for x, I should get 1.5 for y. And that'll help me figure out what p is, because p just tells me how far away the focus is from the vertex. So in the end, I'm just trying to solve for p. So plug in 1 for x, plug in, I'll just put 3/2 in for y. Do a little work here, so 3/2 squared would be 9/4 equals 4p. And if I am, if I take it times a fourth, so I'm going to multiply both sides by a fourth. So p would equal 9/16. So you say 9/16 feet. Probably being better to convert that to inches though. So if you convert it to inches, that's 6.75 inches. Okay, so I need to place that somewhere in here. If that's 1 foot, so a little over halfway, somewhere in there should be the focus, but this is how far away I need to put it. Okay. Let's flip that paper over now. So a little bit more in-depth problem, but once I have my function, my calculator is going to find all the answers for me on this one. So it says that the main cables of a suspension bridge uniformly distribute the weight when it forms a parabola. So if this line makes a parabola, that means all of those cables are holding the same amount of weight. The main cable of a particular bridge is attached to towers that are 600 feet apart. So there's 600 feet between the towers. The cables are attached to the towers at a height of 110 feet above the roadway and are 10 feet. So there's a 10-foot gap in here. So these bars come down. There's a 10-foot gap between the road or above the road and above the road. So a vertical support cable, they're each 50 feet apart. So all these are 50 feet apart. What we want to do is find out how long would each one of those cables be. So it sounds kind of crazy, but really not. I mean, we're just going to write a function. So let's put the vertex right in the middle, and I'm going to put it at the bottom of the road. Okay, so there's my vertex. This parabola does not go through the vertex. It's above the vertex, about 10 feet right here. It says it's 10 feet above that road. So when I write my equation, again, this is an open up, so it's going to be x squared. I am at the center. I'm 0. This is 0, 0. The cable, that first cable is at 0, 10. So this is still, that's why I did x squared. So x minus 0 squared equals 4p. And then for this guy, I would have, if this lowest point on there is 10 feet above, that means it'd be a coordinate of 10. So I go y minus 10. Okay, now I want to find out what's my p. I just need to find a single xy coordinate that I can put in here. Well, from this vertex reference point, I could go right 300 and up 110. So if I go right 300, so it'd be 300 for x, and then up 110, that's one of my points. Put that in for y. Now let's solve and solve for p. So this would be 100. So I got 4p times 100, and then this would be 9, 1, 2, 3, right? Yeah. And what I really want to do, I want to find out what 4p is. I guess I don't even need to know what p, I just want to know what 4p is, because I want to know what to plug in. Because my equation is going to be some number y minus 10. I want to find out what occupies this spot. So I'm actually going to solve for 4p by dividing by 100. So 4p is going to equal 900. So that means I'm going to put 900 in this place. And that's my function. Now if I want to use my calculator to help me with this though, because I'm just going to make a table here. I want to find a table to find all these cable lengths. I'm trying to find the coordinates of all of these points that are at the top. How long are they? How far away are they? So I need to solve for y. So I'm going to first take this 900 over. So this would be 1/900th of x squared equals y minus 10. So 1/900th of x squared plus 10 would equal y. And this will give me the location of those. What I really want to do then, I'm going to have to subtract 10 from all these, but that's okay because this last 10 feet doesn't really count. So I want to find the length and then subtract 10 from it. So first I'm going to make a table. Let's graph that guy. So I'm going to type in y equals, oops, the first one, 1 divided by 900 x squared plus 10, and then make a table. I want to start the table, so here I'm going to go left 300, because if this is 0, that's left 300, it's the first x value I want to know, and I want to go by 50s, that's why I have a 50 in here. Every 50 feet I want to go over. So let's go over here and make the table. So it looks like the first one, that point, so when x is negative 300 and also or 300, it's going to mirror itself. this would be 110 above the roadway. And then if I take 10 away from that, so that'd be 100. And then at negative 250, negative 200, negative 150, negative 100, 50, and at 0. And these would be all the positive values. So 250, 200, 150, 150, and 0. All of these values, I can write them down, but then I got to subtract 10 from it because that cable doesn't go all the way down to the roadway. It's not, even with the vertex, it's going to be 10 above that. So if I might just skip a step here. So this would be 69.4, this would be 44.4, 25, 11.1, 12.8, and then that last one, you wouldn't need one technically. Shouldn't have to have one at the lowest point, yeah. So hopefully that helps. Kind of an in-depth problem, but once we get our function, the calculator does all the work for us.